Okay, now when we're working problems that have to do with calorimetry, okay, it's important that we recognize whether or not the problem is based on constant pressure calorimetry or constant volume calorimetry. And I'm going to start here by looking at a constant pressure calorimetry experiment. Okay, so here I put together a problem that's about as simple as a constant pressure calorimetry experiment can get. So what we're doing is we're taking some substance A and we're reacting it with some substance B to produce C. Okay, now I'm just going to have you assume here that everything reacts in a 1-to-1 ratio. That's going to simplify things in our calculations. We can look at more complex cases later on. Okay, so what do we know right now? Well, we know the amount of each substance, right? We know the temperature increase of the water. We know how much water is there. Now remember, this is a coffee cup calorimeter type of a setup. So basically there's two places where the heat can go. Okay, you have the heat that starts with the reaction is going to have to be equal to the negative of the heat that is picked up by the water. So any heat from the reaction is going to go into the water. Okay, so then how do we figure out the amount of heat that went into the water? Well, we know that the heat that went into the water is going to be equal to the mass of the water, which was 100.0 grams, okay, times the specific heat of water, which is 4.184 joules per gram degree Celsius. Okay, and what is the temperature change? It's going to be 30 degrees Celsius minus 25 degrees Celsius. Okay, in case you don't remember this equation, remember we said that we can calculate the amount of heat that's required to raise the temperature of a substance by using this equation here. Okay, that's all I've used. So, now what do we do? Okay, now we need to go and plug this into our calculator. And I get 2,092 joules of energy. Okay, and if the Q for the reaction is equal to the negative of the heat of the water that's been absorbed, that means the heat of the reaction is going to be equal to negative 2,092 joules. Okay, now it might appear that we have finished the problem. We're not done yet. Remember, the problem is asking for enthalpy, which is a measure of how much heat per mole of substance or per mole of reaction. Okay, so we know that in every cycle of this reaction, we're going to consume one molecule of A, one molecule of B, and produce one molecule of C. Okay, we know that we're starting off with 0.015 moles of A and 0.015 moles of B. And we're going to produce, assuming that the reaction goes to completion, 0.015 moles for C. Okay, so remember, the enthalpy of the reaction, okay, is the amount of heat that is either released or taken in per mole of reaction. So what we're talking about here is 0.015 moles of reactions. Okay, so the enthalpy of the reaction is going to be equal to the heat that was given off, okay, per mole of reaction, which is 0.015 moles, which when we plug it into our calculator gives us 139,467 joules per mole. or we can convert this to kilojoules to make the number a little bit more palatable here. So we'll call it 139.5 kilojoules per mole. Okay, and now that is our final answer. Okay, so that's how we do that sort of problem. Okay, now these types of problems can get more complicated. For example, I may not always give you explicitly the number of moles of reactants. Okay, and I may not explicitly give you the mass of the water. Okay, so let me give you an example. Okay, now, believe it or not, this problem is almost exactly like the problem that we just went over. It's just that there are certain values that we're going to have to come up with through calculations rather than being able to pull them directly out of the problem. Okay, so what we're saying here is that we are taking a certain amount of an acid of known concentration and mixing that with a certain amount of a base solution of known concentration. Okay, and as we've seen in our labs, when you take an acid and a base and mix them together, this is usually an exothermic process, which is going to push heat to the surroundings. Now, since this is a calorimetry experiment, it's not going to push the heat to the surroundings, but rather to the water that's around the molecules. Okay, so there's a lot of information here. We're told about what kind of a temperature increase we see with the water. Okay, and we are told that we need to calculate the enthalpy for the reaction. And of course, we're given the density of the overall solution so we can calculate how much water is actually present there. Okay, so there's a lot here. Okay, so the first thing we want to do is remember what kind of relationships are important in this type of problem. Okay, we know that the enthalpy of the reaction is going to be equal to the heat that is released by the reaction, okay, per mole of that reaction. Okay, so there's two things here we have to figure out. Okay, we got to figure out the heat of the reaction, and we need to figure out how many moles of reaction have taken place. Okay, so how do we figure this out? Well, we know that the heat that is generated by the reaction will be equal to the negative of the heat that is absorbed by the water. Okay, and we know that the heat that's absorbed by the water is going to be equal to the mass of the water times the specific heat of the water times the temperature change of the water. Okay, now, do we have all the information that we need to do this calculation? Well, almost. Okay, we need to know the mass of water. Okay, we are not explicitly given the mass, but we are told the volume. Okay, we're told that we have 50 milliliters of the acid solution, and we have 25 milliliters of the base solution. So we have a total of 75 milliliters. And we're told in the problem to assume that the overall density of the solution is going to be 1.01 grams per milliliter. Okay, and that gives me 75.8 grams of water. Okay, we know the specific heat of water because we can look it up in a table, and we know that the change in temperature of the water was from 22 to 33 degrees. So that's going to be equal to an 11 degrees Celsius change. Okay, so we can calculate now how much heat the water absorbed. Okay, so we're going to take the mass, multiply it by the specific heat of water, which is 4.184 joules per gram degree Celsius, times the temperature change, which was 11 degrees Celsius. And when I plug this into my calculator, I get 3,500 489 joules of heat that's being produced, or that's being taken in by the water. Okay, which means that the heat of the reaction is going to be equal to the negative of that. Okay, so it's going to be negative 3,489 joules. Okay, so now we have a value to put up top here. Okay, but how many moles? Well, let's think about this reaction. We're told that the acid is monoprotic. Okay, so we'll just call it HA, and that it's reacting with calcium hydroxide, okay, which has two hydroxides on it. Okay, so the result of this reaction is going to be water, actually, yeah, two waters, okay, plus whatever the salt is that's produced as a result. Okay, and every one calcium hydroxide is going to react with 2 moles of the acid. Okay, and now that I've written this down, I see that I made a small error here. I had meant for this to be 0.20 molar and this to be 0.10 molar. Okay, so you can see that there's a 2-to-1 ratio, okay, of the acid to the base. Okay, so we've added enough acid to react with all the base. So what I found is helpful here is when we're looking at these types of reactions, I try to find the reagent or the product that has a 1 as its coefficient. And if you can find that, okay, however many moles of that was present, okay, that's the number of moles in the reaction. Okay, so we have calcium hydroxide, so we have 25 milliliters of 0.10 molar calcium hydroxide. Okay, so that means we have 0.0250 liters of calcium hydroxide at a concentration of 0.10 moles per liter, okay, which gives us 0.00250 moles of the calcium hydroxide. Okay, so now to calculate the enthalpy of the reaction, we take the amount of heat that was released, which was the negative 3,489 joules, and we divide that by the number of moles of reaction. Okay, and keep in mind, because there's a 1 right here in front of the calcium hydroxide, that means for every 1 mole of reactions, 1 mole of calcium hydroxide is going to be produced, or is going to be it's going to be reacted. Okay, so then we divide that by the number of moles of the calcium hydroxide, and again we plug this into our calculator. Okay, and once we plug this into our calculator, we get negative 1,395,600 joules per mole, okay, which is the same thing as 1,396 kilojoules per mole. Okay, and that's how we handle that sort of problem. Okay, and of course there's a whole bunch of other different permutations, but the thing that you need to pay attention to, okay, is that when we're looking for the enthalpy of a reaction, focus on what you're trying to find first. Okay, if we're looking for the enthalpy, we write the equation for enthalpy. Okay, that gives us 2 new variables that we need to work with: the heat of the reaction, and then the number of moles of the reactants. Okay, and then we can take a step back with each one of those, okay, until we get to the point where we get the numbers we need to fill in the equations that we were trying to work with. Okay, now in the next video we'll look at some examples of some constant volume calorimetry.